All right, 4.5, comparing and selecting discrete probability distributions. This is all about how do you compare the three different distributions and their expected values, and how would you know when to use which one? Okay, so criteria. So you have the three different probability distributions we've studied. So you have uniform, binomial, and hypergeometric. So what are the parameters and what do they represent? N is the number of items for the uniform distribution. All items are equally likely in a single trial for a uniform distribution. The X represents the value of the outcome. So the example is the outcome when rolling a six-sided die. And you have a range of values for X depending on the situation. The probability for uniform distribution is just 1 over n, and the expected value formula is given right here. Okay, for a binomial distribution, you have n as the number of trials. Okay, so number of trials. Because we're looking at trials that happen independently of each other. P is the probability of our successes. Q is the probability of failures, and they're related because they both have to add up to 100%. Trials are independent. Successes are counted. Okay. X, by definition, is the number of successful outcomes, whereas a uniform it's the value. Binomial, it's the number. Okay. So example, the number of girls in a family of 5. And then you have a range of values, which can go from 0 all the way to n. And there's a probability formula for expressing the binomial probability. And the expectation formula is given here as well. For hypergeometric, very similar to binomial with one key difference. Okay, so n is the size of the population, a couple of changes in the variables, number of trials. A is the number of successful items that are available. Trials, here's the key difference. Trials are dependent rather than independent. Okay, so and successes are counted. So trials are dependent, meaning that if you conduct a trial, it will affect the outcomes of the probabilities of the next trial that you do. So the X is the number of successful outcomes, and X is also given a value between 0 through all the way through R being the number of trials. And it also has its own probability formula as well as its own expected value formula. Now, there is a flowchart here you can study that will help you decide which distribution to use. So you first ask yourself, well, do we have a discrete random variable problem? In this chapter, yes, we do. Are we talking about successes and failures? Then, well, yes. Are those trials independent? Then yes, binomial distribution. Right? So if you have success and failure trials, but they're not independent, then hypergeometric distribution. And if the trials have no success-failure criteria, then check if they're all equally likely, and if they are all equally likely, then uniform distribution. If not, then it's going to be neither of the three that we've studied. All right, so let's look at an example and see which one we need to apply. So example 1, a game consists of randomly selecting a number from 1 to 15 out of a hat. Your favorite number is 13, and you are hoping to select your number. Is this a uniform or binomial distribution? Explain. So we're going to say that this is a uniform distribution. And the reason why is because you're drawing a number from 1 to 15 out of a hat, and when you're drawing a number out of a hat, all of them have an equal chance of being drawn, right? So since each outcome is equally likely, with probability, P of x equals 1 over n, which is equal to 1 over 15, then this is a uniform distribution. Okay, so now how would we rewrite the situation to convert it to a binomial distribution? Okay, so for a binomial distribution, what do we need for a binomial distribution? Well, we need n, we need p, and we need q. Okay, so we know already that the probability p, so the probability of having a success, is 1 out of 15. Okay, which means the probability of failures, Q, is 14 out of 15, because P and Q have to add up to 100%. So we just need a situation. So we just need a situation to get N. Okay, so what is N? N is the number of trials. Okay, so maybe we say, instead of one person drawing a number out of a hat, let's say 5 people. Okay, so for example, 5 people are asked to pick a number from 1 to 15. Okay, so what is the probability that, let's say, 2 will select the number 13? So what is the probability that, based in essence, 2 of these 5 trials will result in the number 13? So that 2 will select the number 13. Okay, so now the problem is a binomial distribution problem. So now you have N. So here, look, we're counting N, number of trials, so 5 people, and the number of successful outcomes. We're interested in choosing 2 of those outcomes being successful. All right, so calculate the probability in each distribution. So for the uniform, N equals 15. Probability is equal to 1 over N. So the probability of 2 is equal to 1 out of 15, and that's equal to 0.0667, or 6.7%. For the binomial distribution, now we have the probability, which is equal to 1 over 15, Q is equal to 14 over 15, and N is equal to 5 people, X is equal to 2. Okay, so 2 successful outcomes. So the probability of X is equal to, using the binomial, C choose X, P to the power of X, P to the power of N minus X. Okay, so the probability of having 2 select the correct number is 5 choose 2 times 1 out of 15 to the power of 2 times 14 out of 15 to the power of 3. And that's going to equal 0.0361, or we can say 3.6%. All right, example 2. At Bob's Burgers, there is 1 in 8 chance of winning a free hamburger. Okay, let's highlight that for a second. All right. Simran bought a hamburger every day for 5 days, hoping to win as many free hamburgers as possible. Is this a binomial or hypergeometric distribution? So since each trial is either a success or a failure, and the trials are independent of each other, then we're going to say this is a binomial distribution. So since each trial is either success or a failure, so you can either win or you don't, and buying a hamburger doesn't affect the probability of buying your next hamburger, so, and the trials are independent. This is a binomial distribution. Okay? But how would we rewrite the situation to make it a hypergeometric distribution? So if, let's say, for a hypergeometric distribution, what would we need? Think about the variables. A hypergeometric distribution. We need an n. Let's go back to our formula. Let's have a look. Okay, so we're gonna need an n. Okay, we're gonna need r. And we're gonna need an a. Okay, so we need to have a size of the population. We need to know the number of trials, and we need to know the number of successful items that are available. Okay, so let's go back down. Let's write down here. We need n, so population size. We need r, which is number of trials, and we need an a, number of successes possible. Okay, so let's rewrite this. So let's give an example. So at Bob's Burgers, in fact, maybe I can type this out for being more efficient. So let's see, at Bob's Burgers, here we go. A customer scratch 3 spaces on a scratch card with 9 spaces. So 3 spaces are what we'll call the free burger, and 6 spaces are try again. So now we have our successes and failures. Okay, so then what is the probability of winning a free burger? Okay, so here now we have 9 spaces, which is our total population, and we can scratch 3 spaces on that card. So we're going to conduct 3 trials, right? 3 trials, and then so out of those 3 trials, you can get a success. So you have three ways of getting a success, which would be my a value, and 6 ways of not a failure. So that would be a total of 9. Okay, so we just now change the problem to a hypergeometric problem. As simple as that. All right, example 3. For a random draw, 20 slips of paper containing people's names are placed into a bin. Barb noticed that 4 of the names were her friends. 5 names will be selected to win a prize, and Barb is hoping at least one of the prizes goes to a friend. Is this a binomial or hypergeometric distribution? Explain. Okay, so we're going to say this is a hypergeometric distribution. Okay, why? Because you have to look at the trials and ask yourself, are they dependent? Okay, so if you draw a slip of paper, so you draw, someone wins, right? And then are there still 20 slips of paper? No, they're now 19. So the probability of drawing in the next success is changing. So this is, let's write this down. So this is a hypergeometric distribution. Okay, since the trials are dependent and have a probability of success or failure. All right, so let's try and rewrite this situation to convert it to a binomial. Okay, so if you want to change this to a binomial, how could we do this? Well, we would need to make the trials independent instead of dependent. Okay, so let's write this down. So to change this to a binomial distribution, we need to make trials independent. So how do we do that? Well, we can just say example, change the wording. So change the wording to include something new. Okay, to include replacement. Okay, when you include replacements, then you're gonna make these trials independent. Okay, so 5 names are drawn one at a time with replacement. Now, obviously, when you replace the name, you're giving that player the next chance to a second chance to, or another chance to win a second prize, or a third prize, or a fourth prize. But that is the nature of trying to make this a binomial problem. You have to include replacement. Right, so let's calculate the probability of success for Barb in each distribution. So in a hypergeometric distribution, you have 20 names, and your population size is 20. 4 of them are successful. A is 4. R is equal to 5. You're drawing 5 names. And we're looking at the outcome of 0. And the reason why is because if you want to know the probability distribution of more than one success, that's a lot of probabilities to calculate. But if you use the indirect method, you just do 1 minus the probability of 0, which is just one probability of calculation. So using this probability formula, P of x equals ACX times n minus A times C of R minus X, and n choose R. Okay, so the probability of having a successful outcome from having more than one of those names, or one or more, is equal to the 100% or 1 minus the probability of having none, of 0. Okay, indirect method, right? Indirect. So that's going to be 1 minus 4 choose 0 times 16 choose 5 divided by 20 choose 5. Okay, so if you don't understand this math here I'm doing right now, so she has 4 friends. So she's hoping one of those names will go to her friends. So we're interested in finding the probability of none of the names going to a friend and subtracting that from one. That way we know the probability of having at least one friend winning. So here, 4 friends to choose from. None of them are chosen, so 4 choose 0. Times 16 other names in that list, because there's 20 in total, so 4 plus 16 is 20. And out of those other 16, those 5 of them will be chosen, and these are not her friends. So that's why we're multiplying these two, multiplicative counting. And we're dividing that by the total number of ways to pick 5 names from a hat. 20, choose 5. Okay, and so that's going to result in 1 minus, this would evaluate on a calculator to be 0.02817, and that's going to be 0.7183, which is equal to 71.8%. Binomial. What if we did this in my binomial way? So the probability of drawing a friend's name is 4 out of 20 names, which is 20%, 0.2. Okay, the probability of failure would then be 0.8. Subtract that from 1, right? And so x is going to be 0, because we're going to do the indirect method here as well. And the number of trials is 5, because we are drawing 5 names out of a hat. So the binomial formula is n choose x, p to the power of x, q to the power of n minus x. Okay, so the probability of choosing at least one or more is equal to 1 minus the probability of not choosing any of your friends. And so that's going to be 1 minus 5 choose 0 times 0.2 to the power of 0 times 0.8 to the power of 5. Okay, and so that's going to be 1 minus 0.3277, and that's going to be 0.6723, or 67.2%. Which distribution would make Barb happier? Well, Barb would be happier with the hypergeometric distribution scenario, since it has a higher probability of her friends winning. And that ends our lesson for this section, our last section of Chapter 4.